In this video, which may be a little long, we're going to look at matrix algebra, and the reason we're doing this is because we're now in the land of systems of ODEs, ordinary differential equations. So we're going to review and or introduce linear algebra concepts. You should have in your pre-calculus 1 class learned some of this stuff for linear systems, but we'll go through it, some of it again anyways, just in case you forgot. Nice review. So the definition of two systems of linear equations are equivalent if their solution sets are equal. Another definition is an M by N matrix is a rectangular layout of numbers from complex plane, which we're not going to be in the complex plane. Sometimes we will be, mostly we're not. Having M rows and N columns. We will use capital letters at the beginning of the alphabet, A, B, C, D, to denote the matrices, and squared off brackets to delimit the layout. So I'll show you what that means in just a minute. We may use large parentheses, but the distinction is not really important. So we're going to start out with a system of equations where we have A11, x1, A12, x2. The x1, x2, x3 are just variables. They're just placeholder variables. The A11, the A12, and all that is the coefficients on those variables. And note how we take this system, which all the way from AM to all the way to the constant of BM. We're going to call this an augmented matrix, which means we're going to augment on or attach on the constants. If this is homogeneous, it would be zeros, which means we didn't necessarily have to need that row. A, M, and then n plus 1. We have n plus 1 because of this constants that we have augmented on. Notice how we do the brackets. We pull off just the coefficients. A11 represents first column, first row. A22, second column, second row. The first number denotes the row. The second number denotes the column. We have n rows and n columns, but Aij represents number of row I and column j. The definition of a column vector. I know I'm going through this fast. Go ahead and pause at any time. Take your notes. Ask me questions in class. Since most of you have already had linear algebra, whether it is with me or somewhere else, that's why I'm going to go through this fairly quickly. The definition of a column vector is a column vector of a size m is an ordered list of m numbers, which is written in order vertically, starting with the top and proceeding to the bottom. At times, we refer to the column vector simply as a vector. Column vectors can be written in bold, usually with lowercase letters. So we'd have U, V, W, X, Y, Z, and we'd have also, you may see this with an arrow above the top, U with an arrow, V with an arrow, W with an arrow, or sometimes you might see with a tittle. This squiggly line is a tittle. I just like saying that too. It's kind of cool. Anyways, going back to our system. We have this system of equations. The constants we would say B with a vector arrow above says that these are my constants. The interior component of the B vector are the M entries as denoted B with an I. We may see it like this. We may see it like this, where 0 to I is less than or equal to M. The solutions to these systems, x bar is denoted this way. It is denoted as a vector, x of 1, x of 2, x of 3, all the way to x of m. These are the numbers, the solutions. We say we have a 0 column vector as if every entry from 1 to m are zeros. The coefficient matrix would have been this matrix up here, but without the augmentation. So it would have just had A11, A22 going all the way across. So let's go and look at an example. So with our system from up above, this is what the coefficient matrix would look like. Notice that I do not have the constants augmented on to the right-hand side. The definition of a matrix representation of a system. If A is a constant matrix of system of linear equations and B is a vector of constants, then we write LS as being the linear system of A comma B as a shorthand expression of the system of linear equations, which we refer to as a matrix representation of the linear system. The augmented matrix we did talk about a little bit. We'll see the augmented matrix, which suppose we have a system of m equations in n variables. The coefficient matrix A with the vector of the constants B are added together. And so we end up having it A, and with this straight line of B, that means notationally, we have an augmented matrix. So if we go back to our system yet again, you can see that this is my augmented matrix. Here's my coefficient, and here is my row of constants. Sometimes you'll see this with a line like that, but not always. Notice the augmented matrix is just that, a matrix that is not a system of equations, and the only connections to the variables is the location of their coefficients in the matrix. In particular, an augmented matrix does not have any solutions. So these are the things that we are allowed to do with matrix algebra, is that we are able to swap the locations of two rows. We will note it row 1 swapped with row 2 as an example, or row I swapped with row J. We can multiply each entry by a non-zero quantity. In other words, I can multiply the entire row by, say, 5 if that helps me, but I wouldn't multiply by 0. We will note it with alpha as being the multiplier, the scalar multiplication of whatever row, then back into that row. We can multiply one row by some quantity and add these two values of these two rows. And then the way we would know that is the scalar A, or alpha, row 1, plus the scalar B, row J, back into row J. We have row equivalent matrices. A and B are row equivalent if one can be obtained from the other with a sequence of row operations. So determine if these are row equivalent matrices. So if I had to do that, what I would do is I can see that this row and this row, so I know that if I take row 1 and switch with row 3, that I have an equivalent matrix in that form. So I know that this row goes up here. Now notice what I have then is I have this middle row. How did I get this middle row? Well, once I switch these two rows, so let me do this, take it with the row 1, switch with row 3, then my A matrix looks like this. 1, 1, 0, 6, 5, 2, negative 2, 3, 2, negative 1, 3, and 4. Now, to get a 3 in that position, I would need to get a 0 in this position. That'd be the easier one to do. Then what I might do is I might do 2 times row 3 plus row 2 back into row 2. So let's see if I get the equivalent matrix. Now notice when I rewrite this matrix A, I have 1, 1, 0, 6. It did not change. And my last row, because I'm putting it into row 2, did not change either. So I like to do with a different pencil. I have this becomes 4, this becomes negative 2, this becomes, let me see, 2 times 3 is 6, and 4 times 3 is, 4 times 2 is 8. So then this becomes 9, 0, and negative 2 and 3 is 4, and 8 and 3 is 11. Now, it does not look like with some row operations I'm going to get the equivalents, because notice how I get 9, 0, 4, and 11, and I have 3, 0, negative 2, and 9. So let's see. If I were to, instead of doing row 3 and row 2, let's look at row 1 and row 2. So let me erase this. Let's do negative 2 row 1 plus row 2 back into row 2. Let's see what happens there. This gives me negative 2. This gives me negative 2. This gives me 0. This gives me negative 12. Now when I add row 1 and row 2, I'm going to get 3. Oh, that looks nice. Negative 2 and 2, that's 0. 0, negative 2, that's negative 2. This is looking really good. And negative 2 minus 3, or negative 12 plus 3 is negative 9. So indeed, these are row equivalent matrices. The theorem of row equivalent matrices represents equivalent systems. Suppose that A and B are row equivalent augmented matrices, such as these. Then the system of linear equations that they represent are equivalent systems. The proof is in any linear algebra book for your viewing pleasure. Reduced row echelon form is a matrix in a reduced row echelon form if it meets the following conditions. If there is a row where every entry is 0, then this row always lies below any other row that contains non-zero entries. The leftmost non-zero entry of a row is equal to 1. The leftmost non-entry of a row is the only non-zero entry is the column. Consider any two different leftmost non-zero entries, the location in row I, column J, and the other located in column T. We're going to give you an example what this looks like. I'm not doing it right now. So the definition of a vector space of n by n matrices. A vector space of n by n is a set of n by n matrices whose entries form the set of complex numbers. This is a definition of the identity matrix. The identity n by m, notice that it is square matrix, is defined by this, which basically says I have a square matrix in which I have ones along the diagonal and zeros everywhere else. The definition of matrix equality, if I have n by n matrices, A and B are equal, written in this form, that means every position are exactly the same. Every position by position, the numbers are equivalent. The definition of matrix addition, we do it by position to position, and we have to have the same size. So a 3 by 3 can be added to a 3 by 3, but a 3 by 2 cannot be added but to a 2 by 3. Definition of scalar multiplication. So if we have an n by n matrix A and the scalar alpha is a complex number, which means it could be a real number, the scalar multiplication of A is n by n, written as alpha A and defined in this form. So in other words, we have this number. We can multiply it through the entire matrix, or we can also factor out that same number. It's kind of nice. So let's see if we can add or subtract. If it is not available to add or subtract, state so. So the first thing I'm going to do if I'm asked to do A plus B is I need to make sure they are the same size, and they are. A plus B is position to a position, so 1 plus 3, or 1 plus 2, which is 3. 3 plus 4, which is 17, and 0 plus 22, which is 22, and 7 plus 6, which is 13. I'm going to look at C and D. C and D are the same size, so indeed I can do that. So the first thing I'm going to do is 3 times C. 3 times C is going to give me 3, 15, 24, and then 3 times 92 is 276. 3 times 12 is 36, so 36, and 3 times 6 is 18. Now I'm going to take and subtract D from that because it's 3C minus D. So I have 3 minus 10. So my 3C minus the D, which is the 3 minus 10 is coming from, is going to be negative 7. 15 minus 14 is 1. 24 minus 7 is 17. 276 minus 2 is 274. And then 36 minus 5, which is 31. And lastly, 18 minus 61 is negative 43. So there we have nice, easy addition or scalar multiplication and subtraction of two matrices. Now notice what I couldn't do is I could not take A and add F because this is a 2 by 2 and this is a 3 by 2. Now here's some things that we get with the vector space property of matrices. We have the additive closure, so if we can add them, then the addition will still be in the vector space. We have the scalar closure, which means if I multiply my matrices by a scalar, I'm still in the vector space. We have the commutative property of matrices, so A plus B is B plus A. The order doesn't matter with addition. Additive associative property of matrices, so I can do A and then do plus B and then add C to it, or I can do B plus C and then add A to it. We actually get the zero matrix. You can get all, so I'm just going to go through this. We have the zero matrix called the zero matrix, so A plus the zero matrix is still A. We have the additive inverses, and so if I take A and the additive inverse, so in other words, I've taken my matrix and multiplied by -1, added them together, I would get the zero matrix. I get the scalar multiplication, which means I can have these two scalars and multiply them together first, and then multiply by A, or multiply by one of them by A, and then multiply the answer of that by the other scalar. We have the distributive property of matrix addition. So I have the scalar and I can multiply it by each one individually and add them, or I can add the two matrices and then multiply by the scalar. We have the distributive property of scalar addition, which means I can add these two scalars, multiply by A, or I can take the scalar times A and the other scalar times A and add them together. last one. If I have the 1, which in matrix multiplication would be a identity matrix, so it'd be a square matrix, then the identity matrix multiplied by A gives me back to the A. Again, all of these proofs are in a linear algebra book if you are inclined to go and read them. Otherwise, just accept those. All right. The matrix dot product. Suppose A is an n by n matrix with columns in this form, and U is a matrix of size n. And then the matrix vector product of A with U is a linear combination. So here's an example. Form the matrix vector product of this matrix with this vector. So following the rule up above, I am doing A. This is A. This is my vector U. A multiplied by U would be 2 multiplied by my first column, which is 2, 1, 1, plus negative 3 multiplied by my second column, which is 3, negative 2, and 5. And then I have my third column multiplied by 0, so negative 1, 7, and 3. And then I have my third column multiplied by 5, or my fourth column multiplied by 5, so 0, 3, and 2. Now what I'm going to do is I'm just going to distribute that multiplier, that scalar multiplier, onto each one of these. So I'm going to do this first one. So this will be 4, 2, and 2. And then plus, this is negative 9, 6, and negative 15. And then 0, that's nice, plus 0, 15, and 10. Now what I do is I add across each column. So 4 plus negative 9 gives me negative 5. So I'm just going to go across each top row of the columns, and I get negative 5. Now looking at the middle row of each column, I have 2 plus 6 plus 15. That's 21, so 23. So that's 23. And then I have this last row in each column. So 2 minus 15 plus 10 gives me negative 3. And there it is. Bam. The theorem system of linear equations as a matrix multiplication, the set of solutions, linear systems AB equals the set of solutions X in the vector equation. AX is equal to B. Again, linear algebra book. Rewrite the system of linear equations below as a vector equality using the vector matrix or matrix vector product. So what this means is I have 2, 3, negative 1, 1, 2, 1, 1, 3, 3, multiplied by my x sub 1, x sub 2, x sub 3, and this is equal to 0, 3, and 7. That's all that means. Definition of matrix multiplication. Suppose A is an n by n matrix, then I can write it in this form. Theorem entries of matrix products. So in other words, suppose A is an n by n matrix and B is a n by p matrix. When I get done, my matrix will be an m by p matrix. Again, we're going to go through an example so I can show you how this looks. So here's an example. Compute the product using the definition above. So this is the way I always do matrix multiplication. I have negative 3, 2, 1, negative 1. This is my A matrix. I like to offset my B matrix. So it's 0, negative 2, 4, and 5. The reason I do that is because I know I'm going to multiply these by these to go in that position. So this will be negative 3 multiplied by 0 plus 1 multiplied by negative 2. And I know that this times this will go in this position, so it is negative 3 multiplied by 4 plus 5 multiplied by 1. I'm going to have this multiplied by this is going in this position, so 0 multiplied by 2 plus negative 2 multiplied by negative 1. And then my last one is this one times this one is going to go in that position. So it'd be 4 multiplied by 2 plus negative 1 multiplied by 5. So my matrix, when I get done, my 3 times 0 is 0, so this is going to be negative 2. I have 12, negative 12 plus 5, which gives me -7. And then I have -2 times -1 plus 0, which is +2. And then I have 8 minus 5, which gives me 3. And there is my matrix multiplication. Matrix multiplication, if I take any matrix and multiply it by the 0 matrix of the appropriate size, then I'm going to get the 0 matrix. If I take my matrix and multiply it by the appropriate sized identity, I'm going to get A no matter which side it's on. We get a couple of things from matrix multiplication. Please note that almost never does this equal, so we say for the most part B times A and A times B as matrix multiplication are almost never equivalent. However, we do get this if we have, I can add these two matrices first and then multiply by A, or I can do A times B and A times C and then add them together. Similarly, if B plus C is on the left side of the matrix D, I can add these two together first, then multiply by D, or I have B times D and C times D. Now notice that order does matter. If A is on the left, then it needs to be left of B and the left of C. If D is on the right, it needs to be on the right of B and the right of C. Order does matter with matrix multiplication. We have this next theorem again. A lot of this stuff is in any linear algebra book. There's a lot of free ones out there if you're inclined. And suppose A is an n by n matrix, B is an n by p matrix, then we have the scalar alpha. Then alpha times AB is going to be equivalent to alpha multiplied by the matrix A, then B, or the matrix A, which gets multiplied by the alpha, which gets multiplied by B first, and then multiplied by A. Oh, we just keep going. So, again, order does matter. If you are multiplying BD, you can do that first and then multiply by A, or you can do AB and then multiply by D. Order does matter. You can't do A times D and then multiply it by B because order matters. Relations of linear dependence. Now we're starting to get into something that may not be familiar to you, which is what linear dependence mean and linear independence. So given a set of vectors, a true statement forming alpha 1, u1, alpha 2, u2, alpha 3, u3 plus ... alpha in u sub n is 0 is a relation of linear dependence on S. If this statement is formed in a trivial fashion, i.e. the alpha sub 1 is 0, alpha sub I is 0, then we say it is a trivial relation of linear dependence, and then we say the vector set is linearly dependent if there is a relationship of linear dependence S that is non-trivial. So in other words, if I can have one column is another column with a multiplication of just a number, then we have linear dependence. Here's linear independence. We say it is linear independent if the case where the only relationship of linear dependence on S is the trivial one. So the only way I can get that is if I am multiplying by 0. So we're going to determine if these vector sets are linear dependent or independent. One of the ways that you can do this is to put it in a row echelon form. So what I'm going to do is I'm going to throw this into a matrix 1, -2, 1, 2, -1, 3, 1, 5, and 0. And then I'm going to do Rref, and there's lots of calculators out there, and you're thinking, how am I supposed to know how to do this without you showing me? It's a bunch of row and column operations. You can pick up any book, and it's going to show you how to do that. So, throwing this into an Rref, I get 1, 0, 0, 0, 1, 0, 0, 0, 1, and what I see is that in each column, there's a 1 in each column and zeros everywhere else. So we know that these are linearly independent. Now I'm going to do the same thing with my second matrix. So this is -1, 2, 4, and 2, 3, 3, -1 and 3, 7, 3, -6, and 4. Once again, I'm going to go out and use an Rref calculator. Pretty much all you have to do is just search Rref calculator, and you're going to get one. I'll also show you, if you're inclined, how to use it on a graphing calculator, but for this class, we won't have to worry about it too much. When I get done with this, I end up with 1, 0, 0, 0, 0, 1, 0, 0, and 0, 0, 1, 0. This is linearly independent because each one of the columns has a 1 in, we call that a pivot, a 1 in those positions. So it is linearly independent, and the relationship between all of these vectors are trivial. Let's take a look at my last example. Again, I'm going to throw this into a matrix. So I have 1, 2, negative 1, 0, 1, 3, 2, negative 1, 2, 2, 4, 4, negative 2, 2, and 3. And my last one is negative 1, 2, negative 1, negative 2, and 0. I just want to take a moment to remind all of my linear algebra students this means that we would not be able to span all of our 4, even though I have 4 entries, because I only have 3 pivots, so the most I could span is R3. Just little thought that you're like, what? Well, if you haven't done that, then that's totally okay. Now, this is the one I really wanted to focus in on. When I RREF this calculator, or this matrix, what I get is 1, and then I get all the zeros underneath it. So I need 1, 2, 3, 4, 4 zeros. 1, 2, 3, 4. My second one is a 0, 1, and then 3 zeros underneath it. Now, my third column has a 1 here, a 1 here, 0, 0, 0. And then my last one is a 2, negative 1, 0, 0, and 0. So this is linearly dependent because I have 4 columns, but I only have 2 pivots. I only have a 1 in a 1 in this first column and zeros below, a 1 in this column and zeros up above. Now you're thinking you have a 1 in this column. Yes, but I have a number above it, so this is not a pivot. I have a negative 1 here, and it's not a pivot because I have this 2 up above. So I have what we call 2 free variables, and this is not linear dependent. So let's talk about the relationship that happens here. So using this, our independent variables are the ones that have these numbers in them without pivot columns. So I say x sub 3 and x sub 4 are free variables. That means my other variables will be wrote in terms of x sub 3 and x sub 4. Taking this first row, I have x sub 1 plus 0x sub 2 plus x sub 3 and then minus 2x sub 4. So x sub 1 is equal to negative x sub 3 plus 2x sub 4. My second row here, let's take this one, I'm going to get x sub 2 is equal to, moving everything over, negative x sub 3, and then plus x sub 4. So what does this mean exactly? Well, if I take negative 3 times the third column, negative 1 multiplied by the third column, add to it the fourth column, I will get the first column. This says that if I take negative 1 multiplied by the third column, add to it the fourth column, I will get the second column. So I know that these are linearly independent. So in other words, what I'm doing is only spanning, by the way, R2, because I have 2 pivots and 2 free variables. Okay, so systems of linear independent vectors and homogeneous systems. Again, we're going to give you a whole bunch of theorems just so I can tell you that we get to do the things that we're going to do. Suppose S is V1 through V sub n, which is a subset of C sub n is a set of vectors where A is an m by n matrix. These columns are the vectors of S. Then S is linear independent set if and only if the homogeneous system, which is the ones we've been solving so far, has a unique solution. The proof is in any linear algebra book. So linearly independent vectors R and S. Suppose that S is the set of vectors, which is a subset of C sub n complex. We're mostly in the real. So a set of vectors, and A is an m by n matrix whose columns are the vectors S. Let B be a matrix in reduced row echelon form, that is row equivalent to A. Let R denote the number of pivots in columns B. Then S is a linear independent set only if n is equal to R. My previous example, my n was not equal to R. I had 2 pivots, I had 4 columns, therefore it is linearly dependent. So determine if the set of vectors are linearly dependent or independent. When the set is dependent, determine the non-trivial relationship of the linear dependence. So what I end up with when I reduce row echelon this thing is I'm going to get 1, and I have 1, 2, 3, 4. 1, 2, 3, 4 zeros trailing behind or below. A 0, 1, 1, 2, 3. And then my last column is a negative 1, 3, 0, 0, 0. We have, in this case, we have 3 columns, sorry, we have 3 columns, but I only have 1, 2 pivots, so I have 2 pivots. So this is linearly dependent, and I know my free variable is my x sub 3. So my relationship is taking this top row. I have x sub 1 is equal to x sub 3, and x sub 2 is equal to negative 3x sub 3. So my relationship I have then is this vector. If I take, so I have x sub 3. Now, there's a 1-to-1 relationship between x sub 1 and x sub 3, so I would put a 1 there. And to get from x sub 2 to x sub 3, it gets multiplied by negative 3. And an x sub 3 to x sub 3 is a position of 1. So that is my relationship. Now, let's come back up here and talk briefly about what this relationship would have been. So we know that in the x sub 3, which is free, right? My x sub 1 is in terms of negative 1 x sub 3. It is not in terms of x sub 2. X sub 3 is in terms of itself, and x sub 3 is not in terms of x sub 4. Plus x sub 4. X sub 1 in the first position is the x sub 1. That's why I'm putting the first position. This was a 2. And my x sub 3, my x sub 2, was a 1, then a 0 because x sub 3 is not in terms of x sub 4, and then 1. So that is the relationship. All right. If you have more vectors than the number of entries in each column, so if you have, say you have 4 vectors and each vector has 3 entries in each column, so there's 4 rows or 3 rows, then we know we're already linearly dependent. So here's our next thing is if the matrix A is this matrix A, I, J, we're n by n matrix, the trace of A, denoted as TR, is defined as TRA is the addition of the diagonals. The trace of a square matrix is the sum of the elements in its main diagonal. The determinant, suppose A, and we kind of talked about this when we're doing the Wronskian, is noted as this det of A, or you look like these absolute values, and it's an element of C defined recursively by this. And you're thinking, what? Well, okay, so there's 2 ways to think about the determinant. Cofactor expansion is one of them, and I don't mind cofactor expansion, which is what all this is. So basically, you take this 3, so the determinant of A would be this 3, and then multiplied by the determinant of the smaller matrix. If you knock out row 1 and column 1, the smaller matrix is 1, 6, negative 1, and 2. And then it's a minus, and again, just accept that it's a plus, minus, if you expand out row 1. So it'd be minus 2, the determinant of. Now I'm going to knock out, let me erase this. I'm now going to knock out row 1, column 2, and my matrix that gets left over is 4, 6, negative 3, and 2. And then it'll be a plus. And if I not plus 3, if I knock out row 1, column 3, so it'd be plus a negative 1, and then the determinant of the smaller matrix, which is 4, 1, negative 3, negative 1. Now, a 2 by 2 matrix is easy. We talked about in the Wronskian. We multiply these 2 and then subtraction of those 2. So I'm not going to do this all. It'd be 3, and then it would be 2 times 1 minus 6 times negative 1, and then minus 2, and then etc. Now this is a cofactor expansion. The other way that you can do a 3 by 3 matrix is doing it like this. So let me just come over here and erase this. I don't personally care which one you use. One may be easier than the other. So what we do is we copy down this first column here. So we have 3, 4, -3. We copy down the second column. So 2, 1, -1. Now what we do is we multiply up and down these values. So I'm going to multiply down in this direction. So I have 3 multiplied by 1 multiplied by 2 plus. Multiplying down here, 2, 6, and -3. And then this last one plus -1 multiplied by 4 multiplied by -1. Now multiplying up in this direction, we're going to get -3 multiplied by 1 plus and multiplied by 6. This next one is plus the -1 multiplied by 6 multiplied by 3. And then my last one multiplying up would be 2, 4, and 2. Now, we're going to sum these up. We're going to get this sum, and I'm going to call this the upper sum. And we're going to sum these up. I'm going to call this the lower sum. And then my determinant is going to be the sum of the lower minus the sum of the upper, and that would be my determinant. It's one of the ways that you may have seen this. I don't personally care how you do these. All right. Again, we talked about the determinant of a 2 by 2. We did that for the Wronskian, so I'm just going to do this really fast. I'm going to multiply these two and subtract this. So this is going to be equal to 12 minus 5 multiplied by -1, which gives me 17. The determinant of this matrix, again, I'm going to probably do it with a cofactor expansion. So I'm going to do -3 multiplied by the determinant of this lower matrix, which is 5, -8, 2, and -5. And then it's plus minus plus. Again, if you want to know why, go check out a linear algebra book. So to be -1, and then erasing this. So I'm going to do this determinant. So it's be the determinant of this lower matrix, which is 5, -8, 4, and -5. And then again, I'm going to erase because I need to do this last one, and it'll be a +1 multiplier. So it's plus, and then 2, knocking out this row and this column, the determinant of this lower matrix, which is 5, 5, 4, and 2. Again, so this is going to be -3 multiplied by 5 multiplied by -5 minus 2 multiplied by -8 minus 1 multiplied by 5 multiplied by -5 plus 4 multiplied by -8. And that should be a minus. It's always a minus when you do a 2 by 2 determinant. And then plus 2, and then it's going to be 5 multiplied by 2 minus 5 multiplied by 4. Now, when I get totally done, this gives me 0. This tells me, by the way, when I get a determinant of equal to 0, that means we have linear dependence. So that's another way to check linear dependence. A lot of calculations to do that. Suppose A is a square matrix of size n, then we get this determinant, which means we can expand out any row I. Notice that we need to pay attention to the pluses and minuses. A minor is a determinant of a submatrix, which is what I did up above, and the determinant of Aij is usually referred to as the minor of Aij. A cofactor is a signed minor. Specifically, the cofactor of A is the -1. This is kind of where the -1, why I have to do plus and minus, or minus and plus, depends on which row or column I expand out. So again, if I expand out row 1, column 1, notice how it is a plus minus plus. And again, we got this shortcut if you are inclined to do a 3 by 3 or smaller. I'm not going to do that determinant again because I'm getting kind of tired of doing this, but I am going to go to this determinant. I am going to choose the column or row that has the most zeros. I'm actually going to expand out this column. Now, just to keep track, this is plus, this is minus, this is plus. This is minus, this is plus, this is minus. So I'm going to expand out column 3 that way. So the determinant of A is going to be equal to 0. Knocking out this row and this column, the determinant of the lower matrix would be 9, -2, 1, 1, 3, -1, 4, 1, and 6. Okay, so now I'm going to erase that. Give me just a moment. Erasing that. So I'm always going to be expanding out there. So it'll be a minus 0. And now I'm going to knock out that row. It'll be the determinant of -2, 3, 1, 1, 3, -1, 4, 1, and 6, which so far is 0. Now, let's do the next one, and it's a plus. So +2, the determinant of. So I'm going to go back over here, and I'm going to knock out, let me knock out that row. I'm going to knock out this row. And when I knock out that row, I'm going to get -2, 3, 1, 9, -2, 1, 4, 1, and 6. My last one. So now I'm going to knock out my last row. And it's going to be a minus, because it's a minus in that position. So it'll be -2, the determinant of. I'll knock out this row. And I have -2, 3, 1, 9, -2, 1, 1, 3, and -1. So really, all I have is this matrix and this matrix with the multiplier of 2 and these smaller matrices. And I can expand out any row or column knowing that I just have to count over from the right. That's the easiest way for me to do it, is counting over from the right using this plus, minus, and then going down the column. So if I were to say I wanted to go different columns, so this is plus, minus. Say I want to go down this column, column 2. So then this would be a plus, this would be a minus, and this would be a plus, would be the multiplier. So +1 or a -1, depending on the position I was multiplying out. Eigenvalues and eigenvectors. Now this is where we really kind of care about this, because we're going to we need to know about eigenvectors and eigenvectors, eigenvalues and eigenvectors for differential equations. So suppose A is a square matrix of size n, and the x vector is not equal to 0, and the entries come from the complex plane. And lambda is a scalar in the complex. Then we say x is an eigenvector of A if this holds true. So if I take x multiplied by the matrix A is going to be equal to a lambda multiplied by x, and then we say this is an eigenvector and an eigenvalue. Every matrix has an eigenvalue, so that's just true. We're going to talk about this in the next section. We're going to convert these linear differential equations into a first-order system and write the system in matrix form. So this is the meat. So I had to do all of that review stuff from before to get to the meat of this section, to tie it into what we're going to be doing from the previous section. Now, previous section, all we did was we set up the system, but we didn't do anything with it. But we didn't put it in a matrix form or anything like that. So now we're actually going to put it in matrix form. So the first thing we're going to do is figure out what would the good be replacements be. Now, from the last video, we know that x sub 1 replaces x. We also know that x sub 2 is x sub 1 prime. And then x sub 2 prime replaces x sub 1 double prime, which replaces x double prime. So these are our equations. X sub 1 prime, which is equal to x sub 2. We have x sub 2 prime, which is equal to -2 x sub 2 plus 5/2 x sub 1 plus e raised to the 2t over 2. Now, again, from our last video, what we did was we divided everything by 2, and then we solved for x double prime and then putting everything in appropriately. So what does this system look like? Well, the system is, it's x sub 1 and x sub 2, and this is prime. This is equal to. So we have the fact that there is no x sub 1 here. So there'll be a 0 in that entry. And we have negative or 5 halves in this entry here, and that should be a negative 5 halves. So let me just change this. It should be a negative 5 halves because I moved that 5 to the other side. So a negative 5 halves is going to go in that position. I have 1 as a multiplier in front of the x sub 2, and I have a negative 2 there. Now this is then x sub 1 and x sub 2. And you're thinking, what did I do with that other one? Well, my other one, since it has t, is going to be 0 here, and then e to the 2t divided by 2 there. And you're thinking, why is there a 0? Well, because we don't see e raised to the 2t in this first x sub 1. This first column, or this first row in this matrix representation represents this x sub 1 prime. So x sub 1 prime is just going to be x sub 2. And there's no e to the 2t. All right, so let's take a look at our next equation here. So our next equation is we have the fourth derivative. So let's start out with the x sub 1 is going to be x. X sub 2 is going to be x sub 1 prime. X sub 3 is going to be x sub 2 prime, which is the x sub 1 double prime, which is the x double prime. This is equal to x prime. And then x sub 4 is going to be x sub 3 prime, which is going to be x sub 2 double prime, which is equal to x sub 1 triple prime, which is x triple prime. So, I know, what? Okay, so then let's start our equations. So from this, and my last one, my x sub 4 prime is going to be, I'm going to solve this thing here for the fourth derivative. This is going to be equal to negative 2 x triple prime minus 3x double prime plus x prime plus x. Helps if I have my signs right, because I need to move these over so that becomes a plus, and these are both minus. That means x sub 4 prime. Now let's put these in its right order. So x sub 4 prime is going to be negative 2 x sub 4 plus 3, x double prime is x sub 3, minus x sub prime, which is x sub 2, and then minus x sub 1. All right, so here's my system. My system is going to start out with x sub 1, x sub 2, x sub 3, x sub 4 prime. Now I'm going to look. My x sub 1 is in terms of itself, okay? And so I'm going to start out with, I have x sub 1 prime, right? So x sub 1 prime is equal to x sub 2. So I don't have anything to put in my x sub 1, so I'll put in a 0. But x sub 1 prime is in x sub 2 and nothing else, so 0, 0. Now, I'd like to put over here, to help remind me, x1, x2, x3, and x4. Remember, it's x sub 1 times 0. That doesn't give me anything. X sub 2 times 1. That's where the x sub 1 prime is. That's where it comes from. Okay. Now, on my next row is how x sub 2 is defined. Well, x sub 2 prime is defined as x sub 3. So 0 in the x sub 1, 0 in the x sub 2, but 1 in the x sub 3, and then 0. X sub 3 prime is defined as x sub 4, 0 in the x sub 1, 0 in the x sub 2, 0 in the x sub 3, and 1 in the x sub 4. X sub 4 prime, I have a negative 1, 3, and negative 2. So I have negative 1, negative 1, 3, and negative 2. And there it is. There is my matrix representation. And we didn't get to that point last video that does it in this video, and that's it for this video. I know it's kind of long because I had to build up to it. The next video will actually start doing stuff with this.